Even though this is the 0th day of separation and mass transfer operations, you already know from your previous classes how to solve separations problems. In order to prove this statement to you, I've went back into the spring 2019 offering of material and energy balances and pulled this problem directly from homework assignment number 4. This is problem statement number 2 if you still happen to have this assignment. I wanted to go back and look at this problem today in order to demonstrate that all separations problems have material balances at the heart of them. And then we'll also talk about how separations as a course is going to go beyond the foundational material that you learned in material and energy balances, and also incorporate some things from phase equilibria, which we'll talk about next class period. This problem statement says 2 liquid separation columns are operating in series at steady state. The feed to the first column is 100 kilograms per hour and is composed of 15 weight percent A, 30 weight percent B, and 55 weight percent C. 2 product streams emerge from the first column. A top stream with 60 weight percent A, 20 weight percent B, and the rest C, and a bottom stream that is fed directly into the second separation column. 2 product streams also emerge from the second column. 1 product stream with 10 weight percent A, 5% C, and the rest B, and another column whose mass flow rate is 20% of the mass flow rate to the feed of the process. The composition of this second stream is 0.2 weight percent A with the rest B and C. Calculate the amount and composition of the feed stream to column 2 after performing a degree of freedom analysis for each column and the overall system. You must specify the unknowns and the equations you are counting. So hopefully you don't need my help in order to solve this problem. If you'd like to challenge yourself, just for a warm-up, see if you can pause the video now and solve this problem yourself. The rest of the video, I'll talk about how to solve this problem and kind of go through the thinking process. The first step in solving any chemical engineering problem is to draw yourself a process flow diagram. So I'm going to do that by drawing a box for each process unit and an arrow for each material stream. So this problem, I have 2 separation columns. So I'm going to label them sep column 1 and sep column 2. And because I know that the bottom stream is going to go into separation column 2, I'm going to draw that one a little bit below separation column 1. Okay, so the feed to the first column is 100 kilograms per hour. I'm going to put that into my process. 100 kilograms per hour. Recall that this 100.0 is not is significant, right? So this is telling me that I have exactly 100.0 kilograms per hour. This is distinct from saying 100 kilograms per hour. If I just said 100 kilograms per hour, that could theoretically mean that I have a measurement that's like 99.8 or something like that. This 100.0 means that there's 4 significant figures of accuracy that I have in this number. Composed of 15 weight percent A, so I'm going to go through and write the compositions. 0.15 A, 0.30 B, and 0.55 C. Notice I've converted from percents to fractions here. You can use either, whichever you're comfortable with. I tend to switch back and forth. I do both for this particular problem. I just decided to do fractions. As long as you're clear about what it is. The only thing I know in this problem, this 0.2 is a percent. So if I convert that to a fraction, I have to be careful to make that 0.002. But we'll get there. Okay, 2 product streams emerge from the first column. A top stream that has 60 weight percent A, 0.60 A, 0.20 B, and the rest C. What does the rest C mean? Well, if I only have 3 components and there is no component D, E, F, G that the problem mentions, so I'm going to assume that I only have 3 components in the entire system, then the sum of everything in this stream must add up to 100%. So therefore, if I have 60 weight percent A and 20 weight percent B, I must, by extension, have 20% C. And usually I try to caution you against trying to do too many things in your head, especially when you're just getting started with doing these problems. But hopefully, as juniors now, you've experienced these material balance problems before. You kind of know the pitfalls of doing too much mental math. And you know that this is not something that you should be afraid of solving for the third composition in a stream of 3 things, given that they have to add up to 1. So this is okay for you to just do in your head and fill in the diagram as you draw it. The bottom stream is fed directly into the second separation column. And remembering from looking ahead, this is the flow rate and composition that I want to be able to calculate. So I don't have a flow rate here, and I didn't put a flow rate on my top stream. So remember that all streams need a flow rate and a composition in order to be appropriately specified. So let's see, in material energy balances, we labeled all of them as N dot or M dot. I'm going to go ahead and do the separations notation. Actually, I'm not going to because it's not a vapor. I'm just going to call this T1. So this is going to stand for tops 1, not T1 because that stands for temperature. Let's call it M1, mass flow rate 1. We'll keep with the MEB convention for now. We'll get into the separation convention as we get there. All right, so I have a mass flow rate. This is going to be in kilograms per hour, just to make sure that we keep our units consistent. And I'll call this flow rate M.2 kilograms per hour. We don't know what it is yet. Remember, that is the point of the problem. Amount and composition of the feed stream to column 2. That's what this is. And I have, I'm going to need mass fractions here. This is going to be X2A, X2B, and X2C. Okay, so just really quickly to talk about separation column 1, the thing that identifies this as a separations problem is the fact that I have changed the composition of my initial stream. So I had 15% A, 30% B, 55% C. Remember I said in the previous video that a separation process is something that changes the composition of a stream or alters the purity in some way. After this stream goes through the separation column, I've got a product stream that is 60% A, 20% B, 20% C. So therefore the composition has changed, and the composition is also going to change in the bottom stream. It's just that we don't know what it is quite yet. And this is the thing that identifies this as a separations problem. So let's keep going with the diagram. 2 product streams also emerge from the second column. 1 product stream with 10 weight% A and 5 weight% C. So I don't know whether it's the top or the bottom. I don't think it matters much. So just go ahead and draw that one on the top. It will matter, by the way, in separations, because typically the top stream is the vapor stream or the light stream. These are all terms that we'll talk about more as the semester goes on. Let's see, I don't know what the mass flow rate is here. So I'm going to call it M3 kilograms per hour. But I do know something about the composition. Right, it's 10% A, 0.10A, X3B, just to keep them in order, and 0.05C. Actually, I do know what X3B is. Again, I can do this in my head. I don't have to belabor the obvious of writing what the variables are. Right? I know if it's 10% and 5%, that means the other 85% must be B. All right, and then I have another stream, which is 20 weight% of the mass flow rate to the process. So this is something else I could do in my head, right? I don't have to write a process specification there. I know if it's 20% of the mass flow rate of the feed to the process, 20% of 100 is 20. And if I want to be consistent about my sig figs, 20.0 kilograms per hour. And the composition of the second stream is 0.2 weight%, which means 0.002 A, and the rest B and the rest C. So I can't do mental math here. I have to keep it as X, I guess this stream would be 4, X4B and X4C. Okay, so again, the goal here is to identify what we want to solve for. And I'm just going to put a red dot by the variables I want to solve. That always helps me keep it clear in my head. I want to obtain what these 4 unknowns are. So the first step after you've done the degree of freedom analysis is to decide where to start. And you decide where to start by performing a degree of freedom analysis. Now, most of you took MEB with me, so you know how much emphasis I placed on degree of freedom analysis. Do not forget how important these are and how much time they can save you. if you don't do a degree of freedom analysis and you just try to start solving, you might try to start solving a system that is not solvable, and you'll get frustrated and you'll want to give up. So let's do a degree of freedom analysis around the first column. So let's just start with DOF for column 1. Remember, to do a degree of freedom, I have to count the number of unknowns and subtract the number of equations that I have for those unknowns. And I need as many, precisely as many equations as I have unknowns in order to have a unique answer. So around column 1, I'm only counting the streams that are coming into or out of column 1. So for instance, M3 is not going to come into my degree of freedom analysis here. So counting up, I've got no unknowns in my input stream. That is completely specified. I've got M1, which is unknown on the top, the flow rate. M2, which is unknown, the flow rate out of the bottom, and the 3 compositions. So I've got 5 unknowns there. And those 5 unknowns again are M1, M2, X2A, X2B, and X2C. What are the equations that I have that I can relate those unknowns by? I always have some material balances. And remember from MEB that you have as many material balances as you have species within the system. So I have 3 components, 3 species, A, B, and C. I can write a material balance around each of them. That gives me 3 material balances. And because I counted X2A, X2B, and X2C as in all of them as unknown, I have an equation that we call the physical constraint in MEB that says the sum of these 3 must add up to 1. So this is an equation I could write. We call that a physical constraint. So minus 1 PC is another equation that we could write, but that is it. I don't have any other equations, any more equations that I can write, so therefore I'm left with 1 degree of freedom. Therefore, if I tried to start solving this problem by looking at separation column 1, I would run into a problem because it's unsolvable. I'd have an equation that I don't have enough information to solve. So it's a good thing I did this degree of freedom analysis before starting with separation column 1. Otherwise, I would have gotten frustrated. Let's try to do a degree of freedom analysis on column number 2. And again, the fact that I have different compositions in the outlet streams is what specifies this as a separations problem. Remember that sometimes I could have one stream being split into 2 in a split point from MEB, and that would just mean that the compositions are the same. So I like to think of it as the difference between taking a glass of lemonade, or taking lemonade from a pitcher and pouring it into 2 separate glasses. That would be a splitting problem, in which case the lemonade is going to taste the exact same. Nothing has changed about it. You're just taking it and putting it into 2 glasses, versus putting the lemonade onto a stove and boiling it for a period of time. That is going to change the taste of the lemonade because you're going to boil off some of the water. The second example, that boiling would be a separations process. So again, this is how separations kind of incorporates itself into material balance problems. But back to the degree of freedom on column 2, I've got the 4 unknowns from the stream that is coming in. I've got M3, which is unknown, so that's 4, X4B, and X4C. So that is 6 unknowns. So plenty of unknowns here. Minus same 3 material balances. Always, I'm going to have 3 material balances for any system, any subsystem within this big system, because I have 3 components. And here I have 2 physical constraints, actually, because I have one from the input stream and one from the 4th stream, or the bottom stream. So 2 physical constraints, but that's still 6 minus 3 minus 2 is still 1 degree of freedom. And I cannot perform an analysis on a system with 1 degree of freedom. So there's still one more thing I could try before I give up and call this problem unsolvable, and that is of the overall system. So if I do a degree of freedom on the overall system, now I'm not counting the middle stream, right? Because I am just drawing a imaginary dotted box around the entire system. And there's only 2 units in the system, so only around these 2 boxes. And anything within this box I don't count, because my system only includes things that are coming into or out of the process. So this is going to help me because this middle stream was the one that was giving me all the problems. That's how I had so many unknowns. I had 4 unknowns just in that one stream. So how many unknowns do I have in the others? I've got M1, the flow rate, M3, the flow rate, that's 2, and the 2 compositions, X4B and X4C. So I have 4 unknowns, and I have -3 material balances, and I have 1 physical constraint from X4B plus X4C plus 0.002 must be equal to 1. So this is telling me I have 0 degrees of freedom for this system, and I can go ahead and solve. So after you have a degree of freedom that is 0, you can go through writing the 4 equations that your degree of freedom analysis told you that you have. So let's go ahead and do that now. So let's write our system of equations. System of equations for the overall system. And we can go ahead systematically and solve those. I just noticed I miscounted here for my, it doesn't change anything, but in column 2, I've got 1, 2, 3, 4, 5, 6, 7 unknowns here, not 6. But just in case you were curious how I got 6, I didn't actually get 6, I got 7. Should be 7. But anyway, there's still 2 degrees of freedom there, and I still can't solve the problem, so nothing changes. My system of equations, so I'm going to start with the 3 material balances. I'm going to do a material balance for each one of my components. So a material balance around component A for the overall system. So these material balances are all going to be of the form, I'm dealing with mass here, right? So it's in minus out is equal to accumulation, because mass cannot be created nor destroyed, so generation and consumption cancel automatically. And accumulation is 0 because I have steady state. Right, so all these material balances are going to be of the form in is equal to out. Remember all these good memories of solving these problems. We're going to do this a lot this semester. So go ahead and brush up if you are feeling at all like you don't think this is familiar. All right, so how much A do I have coming into the system? I have 100 times 0.15. So 100.0 times 0.15 is equal to what is coming out of the system. So I've got A coming out of the system in this stream, M1 times 0.60. I've got A coming out of the stream here. So I don't know how this got erased. This is M3. M3 times 0.10. And I have A coming out in the bottom, so 20.0 times 0.002. And I can't solve this equation because I have 2 unknowns, M1 and M3. So again, I don't really like to start solving equations before I have the entire system, because I want to pick the easiest one, and it's not necessarily true that the first one that you see that is solvable is going to be the easiest. So I'll keep going. So let's do B now. Let me zoom out a little bit so we can see everything. B is 100 times 0.30 is equal to M1 times 0.20 plus M3 times 0.85 plus 20.0 times X4B. Now I've got 3 unknowns in this equation, so I certainly can't solve that one. Let's try C. 100 times 0.55 is equal to M1 times 0.20 plus M3 times 0.05 plus 20.0 times X4C. Same problem here, 3 unknowns in 1 equation. Now at this point, I could look at the system of 3 equations and say that, well, I have 3 equations in the entire system. I can go ahead and solve. Actually, no, that's not true. I don't have the same 3 unknowns. X4B is different than X4C, so I can't actually need the physical constraint. I need the physical constraint to say 0.02 plus X4B plus X4C is equal to 1. So I could at this point look at this system of 4 4 unknowns and I could solve it. Or I could get rid of one of the equations and instead write the overall material balance. Remember that the overall material balance is oftentimes easier to calculate than the pure component material balances. So the overall material balance says that the overall amount of mass, 100.0 coming in, must be equal to the overall amount of mass coming out. So M1 plus M3 plus 20. Now if I'm looking at this system of equations, I would say that, so again, because I don't get confused that I wrote 5 equations and I said they only have 4. These are not independent. So remember, you have as many independent equations as you have unknowns. Because I've written this one other equation, that means that one of the other ones is not independent. So I could use it, I just have redundant information now that is consistent. But anyway, if I use my overall equation and my component A material balance, I have the same 2 unknowns. So the solution procedure here is to solve A and overall together. And I won't take you through the mechanics of how to go through and solve that. That's just a system of 2 equations, 2 unknowns. So solve for one, plug it into the other to solve for the other, and then plug it back in. Or you could that's the substitution method, or you could combine, however you choose to solve them. And you would obtain that M1, find M1, if you're trying this yourself, should be 14 kilograms per hour. And M3 is 66 kilograms per hour. Now, once you have these 2 equations solved, you can then go through and you could solve for either X4B or X4C using the B and C equation. Or you could solve for one and then plug in the physical constraint to find the other. Right, so the whole problem kind of unravels after you figure out where to start. And this problem was interesting because the actual answers that you get when you solve for X4B was negative 1.4 and X4C was 2.4. So mathematically it works out, but one of the main objectives that I had in writing this equation for you is to show you that sometimes you specify something that is impossible. In other words, the mathematics of this problem works out fine, right? So the equations are all consistent, but what does having a composition of negative 1.4 actually mean? It means that you actually have to reverse the flow of B in this separation. So if I go in and I sketch out what my, I'm going to go ahead and just write in what the actual answers are. And you can keep solving this problem. I'm not actually going to go through and solve for what the variables in the middle are. I'm just going to give you the answers. And it would follow along the same procedure. But I wanted to illustrate to you that sometimes you specify something that's not physically possible. So I'm going to write in the answers here, pausing the video. All right, so in green here, I've just written in what the unknown variables are if you were to go through and solve it mathematically. And the point I wanted to make is that why did something go wrong here? If you look at what's coming into separation column 2, I've got 86 kilograms per hour total, and 31.6% of that is component B. So if I multiply those 2 things together, I've got 27.2 kilograms per hour of B coming into column 2. And if I calculate what I have coming out just in the top stream, 66 times 0.85 is 56.1 kilograms per hour of B in stream 2. B in stream 2. So this is obviously not possible. I can't have more coming out than I have coming in, especially when I have another stream. So this is why I have to mathematically make up for this by saying minus 1.4. The idea, what I'm trying to get across here is that I have laws of the universe that I have to obey, right? So I have to have material balances that are closing. I also have laws of thermodynamics that I have to obey. In other words, if I were just to specify as an engineer that I want 100% of my stream to be component A and 0% to be B, 0% to be C, that would be perfect, right? Because then it'd have a pure component. But a lot of times you can't do that. You can't, there's a limit to how far you can go. So a lot of this class is putting material balances together with what phase equilibria tells us is possible. And we merge those together, and that is how we get a separations problem. So hopefully you enjoyed this review of material balances. The next class, I'll give you a short review or a crash course if you haven't actually taken the course or taking it now for phase equilibrium. And after that, that will give us a good foundation to move forward and start designing some of these separation processes. See you next time.